And the more we push science and the more we sort of, as industry, get that out there, then the more adoption will occur. And from our standpoint, as we think about the democratization of data, what we're trying to do is move people away from a one-size-fits-all, just push the science, get it out there, and start to think about, almost akin in some ways to almost the kind of Moneyball concept, if you've read that book or familiar with Billy Mead. Think about positioned players in the ecosystem and how they contribute to the dissemination of whether it's the actual science, whether it's in the clinic, how behavior actually is occurring. Think about the position that those people play. So from our standpoint, what we're trying to do is move away from a one-size-fits-all push to start to think about who are the physicians that have the experience, and what is that experience, and how can we empower them with the right tools so that they can spread that information in their network and with their peers, and they can be the drivers of the anecdotes, the science, the information, all of the key things that are very relevant. That's certainly, from our perspective, this is sort of how we've thought about the role that we can play in this ecosystem.
Yeah, and I'm happy to share our perspective at Foundation Medicine. I think, Rob, what you're bringing up is this sort of fundamental conflict between observational data and sort of the traditional gold standard of medicine, the randomized trial. And I think that, at least from my perspective, there are a couple of things that are worth considering. One, I think we know from work like Johnny and others here that not even the RCT is infallible. But second, that the tenability of randomization of every of these permutations, we're going to reach a limit where we simply cannot randomize in every different combination, every specific genomic permutation. When you've got 10 patients that match one particular, let's say, subtype, how do you randomize every group of 10 patients and learn from them? So I think that there will be a necessity that we find a way to...
Okay. All right, so I figure I have to start with a review because you understand quarters since the last had lectures for me on quantum mechanics. On the other hand, they can't spend the whole quarter doing that. What I want to spend the quarter on is the applications of quantum mechanics, not the technology, but the physics problems. And the basic physics problems that I want to go through this quarter are those for which quantum mechanics was originally discovered, invented by Einstein, Heisenberg, Schrödinger, Pauli, all those people, namely atoms, electrons. I'm going to do atoms first. Okay, how can I do atoms first before I do electrons? Electrons are part of atoms. So I will do a little bit about electrons. It's almost nothing, but just enough to be able to write down the basic equations of the hydrogen atom, discuss the hydrogen atom a little bit, and then move on to further investigations of the electron. And when we say the electron, we're actually studying a class of particles, not just electrons. A wide class of particles behave like electrons. Mu particles, quarks, other things like that. And then the photons. So it's going to be atoms, electrons, and photons. But one of the themes that will occur symmetries of nature and how symmetries are realized in quantum mechanics, how symmetries are represented in quantum mechanics, and what they tell us about the quantum mechanics system. Symmetries in quantum mechanics are an extremely powerful tool, which, now I'm going to tell you what a symmetry is. If you don't know what a symmetry is, it's okay at the moment. But let's begin very, very lightning review of the last quarter of quantum mechanics. First of all, the whole story begins by asking how do you represent the state of a system. So you back a step and ask, what is a system? But I'll assume you know what a system is. And how do you represent the states of a system? In classical mechanics, the states of a system are represented as points in phase space. Quantum mechanics, they're represented by state vectors. The idea of a vector